so for our plug in everything and solve questions, so first we need to figure out like which equation we're going to use. If we're solving for force, then we're going to use the FG equations. So either this one or possibly the just mg, but most of the time it's this one because we won't know little g at that point. And then another word for the force of gravity is called the weight. So when I ask you for weight, that is the same thing as if I asked you for the force of gravity. For acceleration due to gravity, that's talking about little g. So we're going to use the little g equation, big G m over r squared. And you'll notice that there's only one mass. For the force of gravity, both masses have a matter for the force of gravity, whereas in this one, there's only one mass. So which mass is it? It's the bigger mass. So if we are talking about like the acceleration of like a book falling down to the earth, right? We're going to use the mass of the earth, not the mass of the book. And then what else is acceleration due to gravity called? It's called the gravitational field strength. You need to know that that is the same thing. Those both mean little g. Like that. Difference between weight and mass. So mass or weight is actually a force. So this is going to depend on gravity. So it will change on like different planets, right? So if I go to the moon, I have a different weight than if I am on Earth or Mars, etc. My mass will be the same anywhere. My mass isn't going to change if I go to the moon. That's just how much mass I have. A 1,200 kilogram object is on the surface of Venus and has a radius, which has a mass of this and a radius of this. What is the acceleration due to gravity here? So that's little g. So we're going to plug in gm over r squared. Big G we know. The mass is going to be the mass of Venus, not the mass of the object. Because again, the bigger mass or the mass of the thing that is creating the acceleration due to gravity over radius squared. And then you just type this into your calculator and you get the gravity, or acceleration due to gravity is 8.9 meters per second squared. The mass of the object on Venus, well, its mass isn't going to change. It's still going to be the 1,200 kilograms. The weight of the object, weight is asking for the force of gravity. So I could plug into the m1, m2 over r squared. I would be plugging in exactly like I did here, but you would be adding the m2, which is the mass of the object. Or you can just do the mass of the object times the gravitational acceleration, which is what I'm going to do to save time. How much is it? 9.8. It's 8.9. And that's going to give me a weight of 10,697 newtons. Now, what would happen problems? Well, the first thing we need to figure out is what is it that's changing and by how much. And then once you know that, you plug in, like if something's doubling, tripling, etc., figure out how much the force would change, so how many times bigger or smaller. And then last step is to actually multiply your old force by the factor to get the new force. When is G 9.8? When it is on the surface of Earth. So a lot of these what would happen problems are talking about little g, and they're comparing it back to Earth, so then your old g is just 9.8, because that is comparing it back to something on the surface of the Earth. If I want a big gravitational force, so gravitational force is g m1 m2 over r squared. If I want big number here, I want to multiply by big number, so big masses. And I want to divide by small number here, so I want a small radius close together. And then the opposite. If I want a small force, I want to multiply by small masses, and I want to divide by big numbers to get the smaller force out. So small masses far apart would be a small force. Which has a greater impact on the force of gravity and acceleration, mass or distance? Distance, because the r is squared. So if you think about, like, if I were to triple the mass, that would be a factor of 3 times bigger. If I were to triple the radius, that would be a factor of 9 on the bottom. So it gets counted almost like twice. Tell by what factor the force would change if the following changes were made. So mass of both objects is doubled, that's 2m over r squared. That would be times 4 over 1, so that's just 4 times bigger. If the distance is doubled, you're assuming everything else stays the same. So that would be a factor of 1 on top and 4 on bottom, so that would be 1/4 smaller. Mass of one object is doubled and distance is doubled. So that's a factor of 2 on top, 2 squared is 4, so that's times 1/2. smaller. And distance is halved, so m over 1/2 r squared. Be really careful here because some people just go, oh, 1/2 squared. That's not what's happening. We have a 1 on top and the 1/2 squared goes on the bottom. 1 over 1/2 squared is not the same thing as 1/2 squared. Also be really careful putting this in your calculator. You have to have the parentheses when you're dividing by a fraction because this is going to give me times 4 bigger. And then a quick check for yourself, if you had gotten 1/4, if the distance is halving, that's getting closer together, which means you should be getting a bigger force, not smaller. So times 4 at least was reasonable. If both masses are doubled and the distance is halved, that would be a 4 on top and 1/2 squared on bottom. Again, careful with parentheses in your calculator because that's going to give you times 16 bigger. And it's getting a lot bigger because you're doing 3 different things that make the force bigger. More mass, both masses are increasing, and you're getting closer together. So it's okay that it was a lot bigger. You weigh 40 newtons on Earth. If you go to a planet with twice the radius and triple the mass, so 3 times the mass and twice the radius, what's going to happen to that weight? That would be times 3/4. Now 3/4 smaller is what's happening to it. I want to know what the actual weight is. Well, if this is my old weight or my old force, and it gets 3/4 smaller, you just multiply, and that's going to give me, I did 30, but that's a 40 right here. Oopsies. 40 times 3/4 gives me my answer of 30. 6. In the diagram below, at which point would a spacecraft traveling from Earth to the Moon experience a gravitational force from the Earth equal to that of the Moon? So I want to know at which of these points would it feel an equal force towards the Moon as it feels, towards the Moon as it feels towards the Earth. It says that B is a halfway point, so a lot of people are tempted to just go like, oh, halfway. But that's not going to be the case here. At point B, it's actually going to feel a greater force towards the Earth. And the reason why is because the Earth has a bigger mass. So it would feel a force towards the Moon, but it would feel a bigger force towards the Earth, so B would not make sense. If you're at A, it definitely feels a bigger force to the Earth because the Earth has more mass and you're closer to it. So the point that makes the most sense is C. Because C, at this point, you're close to the small mass and you're far away from the heaviest, which at least will balance out. So C was your answer because the spacecraft is further from the Earth and it's more massive. And so like how I explain it with my reasoning is saying you're close to the small mass and you're far from the big mass, which is going to cancel out. Because the big force is big masses close together, and a small force is small masses far apart. So if I have small masses close together and big masses far apart, that balances out. Gives me like a medium force for each. Number 7, we have a mass that's 2.5 times that of Earth's and same radius, so that would be times 2.5 bigger. And I want to know what G would be near the surface. Well, G in Earth is 9.8, and if it gets 2.5 times bigger, that's going to give me 25.5 meters per second squared. Steel balls exert a gravitational force on each other. As the mass of one is doubled and the distance is reduced in half, the gravitational force between them is, so twice the mass and 1/2 the radius, or 1/2 the distance. That's a factor of 2 over 1/2 squared. Make sure you're careful with parentheses around this because that would be times 8 bigger, so D. How would the gravitational force between the Earth and the Moon differ if the Moon was twice as far away as it is now? So if I have twice the distance, then that's going to be 1 on top and 4 on bottom, so that's getting 1/4 smaller. So that's decreasing by a factor of 1/4. What would happen to the gravitational force if the mass and its sun were both doubled? So if you have like something like this, and now you have twice the mass and twice the mass, so you are changing the system, doubling both masses, that would be times 4 over 1, which is just increasing by a factor of 4b. Which line would make you weigh half as much, so I want to end up with times 1/2. If I go to twice the distance, a lot of people put this one. Actually, if you go to twice the distance, r gets squared, so that would be times 1/4. If I go to half the distance, that would be times 1 over 1/2 squared, which is times 4. But you could have crossed off C immediately, because if you want to weigh less, then you would go farther apart, not closer. Closer would give you a bigger force. Take away half of the Earth's mass. Well, if you take away half, you're halving the mass. So 1/2 mm over r squared would just be times 1/2, which is what you want. So B was the only answer that made sense. A, maybe if you don't do the math, makes sense, but actually the 2 gets squared, so it's 1/4 smaller, not 1/2. The reason why your weight at the surface of Saturn, which is much bigger than Earth, is similar to that on Earth is because, so if something is much, much bigger, I should have specified that, like whether this was mass, but I meant more mass. So the way that we can have more mass but still have the same like little g or the same like weight, or I guess FG here. So how I can have a much bigger mass but have the same weight is if I have a bigger radius. Think about your weight is the force of gravity equation. So you can have a much bigger number here, but if you're also dividing by a bigger number, then that can cancel out. So see, Saturn is much more massive, but you are farther from the center, which means bigger r. So big mass and a big radius can actually balance each other out. In fact, radius counts more, right? So if you were to have twice the mass, or 4 times the mass, twice the radius would cancel that out. So C. As an astronaut travels from the surface to Earth to a position that is 4 times as far away, so that's 4 times the radius, and obviously the astronaut's mass isn't changing, nor is the mass of the Earth. That would give me times 1/16. So the force of gravity is going to decrease, which is talking about weight decreasing. It would not increase, it would not remain the same. The mass would not decrease because it stays the same. Mass remains the same. We actually didn't need to do any math at all. The Earth has a mass that is 81 times the mass of the Moon. So this is like 81 m and this is m. And I'm saying if the Earth has a force F on the Moon, then what is the force of the Moon on the Earth? Well, we're talking about 2 objects, the gravitational force between them, so it's F. If you're saying, wait, but if you do 81 m, blah, 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 that is if I change the system to make it 81 times bigger. All I'm saying is that this is a bigger mass. It doesn't matter if I were to plug in 1 kilogram times 81, or if I plugged in 81 times 1 with my M1, M2, or M1, M2 here. It's the same force. When you're doing the what would happen, that's if you're saying I had M and now it's 81 M, if you're changing it. Here I'm not changing it, I'm saying these 2 objects, what's the force between them? Same force. 2 objects are attracted to each other with a gravitational force of 4 newtons, that's my old force. The mass is doubled and the other mass is tripled without changing the distance. That's a 2 times 3 on top, so times 6 on top. And then it's getting 6 times bigger. If my old force is 4, you make it 6 times bigger. That gives me 24 newtons. Satellite B is 3 times more massive than satellite A. Which satellite experiences a stronger gravitational force with its Earth? So I'm saying these 2, their force compared to these 2 force. Now these 2 have the same force of each other. If I say this is F, and then this has to be F. Now if I go to B and the Earth, now I'm changing, right? It's not the same 2 objects again. It's B and the Earth. So these 2 will share the same force with each other, but it doesn't have to be the same force that these 2 share with each other. In fact, if you have 3 times more mass of this satellite, then you would have 3 times the force. So B would feel a greater force than A would. So B, because it has more mass. Now some of you are sitting there and saying, wait, but satellite mass doesn't matter. Well, when we're looking at all of our equations, this one, only one mass matters, this one, only one mass matters. Here, the period doesn't have mass in the equation, but the period depends on V, which only one mass matters. But if you go to the force of gravity, both masses matter. So if both of these masses are in the equation, then tripling the second mass would triple the force. Here, if I'm talking about tripling M2 or the second mass, that's not going to affect it because I only care about that first mass, the mass of the planet or whatever it's going around. When an object is 3 Earth radii away and it weighs 100 newtons, when I go to 6 Earth radii away, I want to know what it would weigh. So I'm changing the distance. If I'm going from 3 radiuses to 6 radiuses, that's a distance times 2. And now it's just plugging in, okay, if I go to twice the radius, that would be 1/4 smaller. And if my old force is 100 and it gets 1/4 smaller, my new force is then 25. Jupiter has a mass of 300 times the Earth and a radius 11 times larger than the Earth's. What's the acceleration due to gravity? This is a what would happen. 3 times the mass, 11 times the radius. That's 300 and 121. And then that's how many times bigger the acceleration is going to get. I want to know what the actual acceleration is. Well, I'm comparing it to Earth, and Earth's acceleration is 9.8. So you just multiply, and you get 24.3 meters per second squared would be your new g. Hypothetical planet has 9 times the mass of Earth and same gravitational field strength. What would you have to do to r? Like, what is this r in terms of the other r? So how many times bigger or smaller is it, basically? If I want to get the same gravitational field strength, then that means I need to multiply by 1, because multiplying by 1 is the only way it stays the same. If you multiply by 2 or 1/2, you're getting bigger or smaller, etc. So right now I have a 9 on top. If I want to stay the same, then you need a 9 on bottom, which means that you need to triple the radius. Your answer is 3 times the radius of Earth. Hypothetical planet has a mass 8 times that of Earth and half the acceleration due to gravity, so I want to end up with 1/2. And I want to know what happens to r then. So right now I have 1/2, right now I have 8. I want to end up with 1/2, which means on the bottom I would have to have a 16, because 8 over 16 is equal to 1 over 2. If I want 16 on bottom, that means I need 4 times the radius, so 4 times the radius of Earth. Typical white dwarf star was once an average star like us. It has this radius and this mass, gravitational field strength. That's asking for little g, so gm over r squared. And this is straight plug-in. So then you get your gravitational field strength. Ooh, big number. Oh no. Okay, we'll leave off the decimals. That's enough digits for us. So this has a huge gravitational field strength compared to Earth's 9.8 because it has a huge mass in a very, very small radius. You're multiplying by big numbers and dividing by small numbers, so we do get a big number out. Apple hangs on a tree on the Earth, which of the following statements is true. The force on the force on the apple is greater than the force on the Earth. The force of the Earth is greater than the force on the apple. The force on the apple is less than the force on the Earth. The force on the apple and the Earth are equal to each other is the correct answer. So I have the apple and I have the Earth. I'm asking for the force between them, the gravitational force between them. It's the same two objects. I'm not changing anything, so it's the same force between them. Two objects each with this mass produce this force. What is the distance between them? So I have two masses, F, looking for R. That's our F of gravity equation. So 3.7 E negative 6 equals 6.7 E negative 11, 2,500 over R squared. Now, we cannot ignore G here because this is a plug-in problem, right? We're not doing like what would happen. I'm plugging in real values, so I have to plug in all my values, including G. First thing you want to do is multiply the R squared up. That cancels out. And now I have R squared times this number equals, I put this in my calculator and I got 4.187 E negative 4. And then down here, bring this down. Now the next step is we're trying to get R by itself, so we want to divide this number over. Sorry, this is getting squished. So that gives me R squared is equal to 113.7. Now that is not my answer. That is what R squared is. I want the R, so I take the square root and I get my answer is 10.64 meters. Two objects have a force F. If each mass is tripled and the distance is cut in half, that would be a factor of 9 on top and 1/2 squared. Make sure you plug in with parentheses. That's going to give you times 36, so it's getting 30. The new force would be 36 F, 36 times the old force. If the moon was only half as far from the Earth as it is now, what would the gravitational force be? So first of all, half is getting closer. If it's getting closer, that should be a bigger force. So I can cross off anything that's getting smaller because I know I get a bigger force. And now we just plug in, okay, same masses but half the distance. That's going to be a 1 on top and a 1/2 squared on bottom. Put that into your calculator with parentheses, you get times 4. So 4 times its present value. This bonus, you can skip it if you want, but if some of you want these extra points on the test. So the force between two objects is 27 newtons, and they are 2 meters apart. Now they have a force of 3 newtons. How far apart are they now? So first of all, if you're getting a smaller force, you got farther apart. So I'm going to make a note just to check at the end. I know that they have to get farther apart. Now 27 to 3 is you are 1/9ing the force. And I'm saying, what am I going to have to do to R if I keep the same masses, because it doesn't say anything about changing masses, and I want to end up with 1/9 the force. So you know you're going to need to triple the radius. If my old radius is 2, and I have to triple it, then my new radius should be 6 meters. The only two things that orbital velocity and therefore period depend on is the radius and the mass of the thing in the middle. The thing that is being orbited around, that other things are orbiting around, the thing that's in the middle. The period is the time for one full orbit, so the time it takes to go around once. R is measured from the center of one object to the center of a second object. So sometimes I just give you the orbital radius R, and sometimes you have to add the radius of the planet in order to find R. And how you know when you need to add is if I only give you, if you're given the height / sometimes it'll be called the altitude above the surface of the planet. Keyword surface there. So if I say something is, I don't know, 1,000 meters above the surface of the planet, that's not your orbital radius. You would need to add 1,000 to the radius of that planet in order to get that R. If I say it orbits at this radius, then you're good. That's your R. If you want the fastest orbital velocity, so first of all, look at your orbital velocity equation. If I want a big velocity, then I want to divide by small numbers. So I want a small orbital radius. I want a big mass on top. This mass is the mass of the thing it's orbiting around, in this case a planet. So I want a big planet mass. And the second mass, the mass of the satellite, does not matter. Has no effect. So I'll just say it doesn't matter. If I want a long orbital period, if you want it to take a long time, then you want it to go slow, right? You want a slow velocity or a small velocity. If you want a small velocity, you want to divide by big numbers. You want a big radius. You want to multiply by small numbers. You want a small planet mass. And again, we don't care about the spacecraft's mass. Blah, blah, blah. We want to find weight, which is asking for force or gravity at this height above Earth's surface. That is not your R. That is the distance above the surface. So I'm going to have to add the 300,000 to the radius of the planet. In this case, it's Earth. So add it to the 6.37 E6. That's going to give me my radius. I think it's 66,700. Yeah. So 66,70,000. Obviously not saying that number correctly. That number right there. And then we're going to plug into our force of gravity equation. So G, M1 is the mass of the astronaut, M2 is the mass of the Earth, or if you switch those, it doesn't matter. It's the same thing, whichever way I put it, divided by this radius squared. And you'll get 675 newtons. So we saw videos of astronauts that look like they are weightless. They definitely feel weightless. And it's not that their weight is so small, because on Earth they would be weighing like 750-ish, and now they're weighing 675. So I weigh a lot more on the moon than I do at this height. And on the moon, you're still falling back down to the moon. So it is not that the force of gravity is so small. It is not that you're so far away that gravity is just like small enough that you can't feel it. Absolutely not true. In fact, it's like 90% of the weight they would feel on Earth. What's happening is that the space shuttle is constantly falling down. It is constantly falling down towards the Earth. It's just moving so fast sideways that by the time it falls down, you can see how it's falling down, it's just moving so far to the side. Now it's being pulled to the center. Now down is to the left in this diagram. but again, it's moving so fast that by the time it's gone to the left, it's all the way down here. And then it just keeps doing this. It's moving so fast to the side that when it falls down to the earth, it's actually missed the earth. It's on the other side of the earth and keeps going and going. So they feel weightless because they are falling. They are constantly falling to the earth. The same way when you're in an elevator and it starts to go down, you feel that moment where you're like belly flips because you feel weightless. Or if you're in a car or roller coaster and you go like over a hump, you like get off your seat for a second. You're like both falling down, so you feel weightless. That's the idea. Acceleration due to gravity is little g. So at that point, we're gonna plug in. We're gonna plug in the mass of the Earth because it's the mass of the Earth that is creating the acceleration due to gravity. And we want to make sure we use the correct radius that we just found. So that one gives me 9 meters per second squared, which is reasonable because it's 9.8 on the surface. I go a little bit higher, I get 9. So a little bit less, but still lots of acceleration due to gravity. Orbital velocity, square root of gm over r. We know g. We know the radius. It's the same radius because we're at the same height. And then we need to be careful with mass here. We want the mass of the thing we're orbiting around, which is the mass of the Earth. Mass of the space shuttle doesn't matter in this case. It did matter for the weight, because M1 and M2, but everything else, it doesn't matter. So you would get 7750 here. And then how long it takes is asking for the time or the period. So you plug into your period equation, 2 pi radius, we know, divided by velocity we just found, and you should have gotten 5407. 27, a 260 kilogram satellite orbits the moon at this altitude above the surface. What is the period of the Earth's orbit around the moon? So this is not my r. To find my r, because this is the distance above the surface, I would have to add to the radius of the moon, which I gave you. That gives me my radius is the left. How many zeros is that? 5? Okay, so this gives me my radius. It would be 1,800,000. Yeah. And then looking for period. To find period, the 2 pi r/v, I would need velocity first. So I'm going to plug into my velocity equation. And we want to use the mass of the thing that is it's going around. It's going around the moon, so we'll use the mass of the moon, the 7.35 e22. This mass of the satellite doesn't affect the velocity or the period. And then plug in your r, so square root of g, mass of the moon over this radius, and you get 1654 meters per second for your velocity. And then last step is actually find the period, what it asks for. So 2 pi radius over the velocity we just found is going to give me a period of 6,837 seconds. One of Saturn's moons is named Mimas. I don't know how to say that. It has this orbital radius. Here I gave you r. This orbital period, t, and I want to use this to find the mass. So all I have is t, r, and I'm looking for m. If you notice, there's not an equation with these 3 letters in it. So what we're going to do is we're going to use the t equation because I have t. So the t equation is 2 pi r over v. Now what I can use this to find, if I have t and r, then I can find the velocity. So we're going to plug in the 82,800 equals 2 pi 1.87 e8 over v. When your unknown is on the bottom, you need to multiply it up like this, and then we can divide the 82,800 over, and that's going to give me my velocity is 14,190 meters per second. Now that's not my answer. That's just the first step because that was all I could find with the period. Now that I have velocity, I can find my mass by using my velocity equation, square root of gm over r. Now it's just going to save you so much time and typing to rearrange first and then plug in your numbers. So first thing we would need to do, if we're trying to get m by itself, sorry, I'm just trying to point out this is what we're getting by itself. the first thing we need to do is get rid of the square root. To get rid of a square root, we do the opposite of square rooting, which is squaring. So when I square the left side, that's going to give me v squared. And when I square the right side, the square and the square root cancel out, and I'm just left with what was inside. Now I have v squared is gm over r. I need to multiply that r up, because again, we're just trying to get rid of things that are keeping the m from being in the way. So that gives me r v squared equals gm. And then last thing to get m by itself is divide g over. And then we actually plug in our numbers, r times velocity squared over g. And that's going to give me a mass of 5. Someone said they have 5.6. I have 5.4. But if you have 5.6, then maybe you did it right. I'm going to go with what I have, but if you have 5.62, then those people are probably right. 29, space shuttle orbits the Earth in a circular path where the gravitational strength is this. That's my little g. What is the shuttle's orbital radius? So g is big G m over r squared. Can plug in our values. We're talking about around the Earth, so the mass of the Earth, which I have been given, over r squared. So that gives me 8.68 equals 4.0, I think it's like, yeah, just leave it like this, over r squared. I just put these two numbers in my calculator. Now, your unknown's on the bottom, so let's multiply that r squared up. And then to get r squared by itself, now I divide the 8.68 over. That's going to give me r squared is 4.615e13. Not done, that's what r squared is. I want r, so I square root, and I'm going to get 6794040. And that's your radius. A space station that has 10 times the mass of the shuttle in A orbits at the same altitude. How does the orbital speed of the space station compare to the shuttle? So same altitude, you've got the the shuttle, and then you've got like the big space station going around. So when we're looking at the orbital speed, that only depends on two things: the mass of the planet, or the thing you're going around, and the radius. They're both going around the same object at the same radius, so it will be the same speed. What's changed is the mass of this second object. When we're looking at velocity, the mass of m2, or the second object, the thing that's actually going in a circle, doesn't matter. If the space station moves to a lower orbit, how will the velocity and period be affected? So a lower orbit would be a smaller r. So if you look at this, what happens when you divide by a smaller r? Well, dividing by a smaller number is going to make this be bigger, so you would have a faster velocity. And if you have a faster velocity, then the time it takes to go around would be less, so a shorter period. Faster v, shorter period. So v, by the way. Two moons orbit the same planet at the same radius. Moon A has triple the mass of Moon B. So, helps to draw a picture. I've got Moon A and Moon B. And Moon A is bigger than Moon B, and they both at the same radius around the same planet. That's a really big moon compared to the planet, but that's okay. And I'm circling everything that's true, so it's possible there are multiple answers. A says the force between Moon A and the planet is greater than the force between Moon B and the planet. So the force between these two compared to the force between these two. If you look at your force equation, it's g m1 m2 over r squared. So here, both the mass of the planet and the mass of the moon matter, and the radius. They have the same first m, they've got the same r, but that second mass, the one that sometimes matters and sometimes doesn't, in the FG equation, the second mass does matter, so it would be a greater force if you have a greater second mass. The acceleration of Moon A towards the planet is greater than the acceleration of B towards the planet. Well, acceleration is gm over r squared, where this would be the mass of the thing that is like pulling it down, right? So in this case, not the mass of the moon, but the mass of the planet that would create the acceleration towards the planet. They have the same mass of the planet because they're going towards the same planet, and they're at the same radius, so this would be the same. So that's not true. Orbital velocity, square root of gm over r. Again, they're around the same planet. That mass is the mass of the planet, so v would be the same. The period, well, if they have the same velocity at the same orbit radius, then the period would go do the same thing. Two identical objects go to different planets. A has a greater mass than B, but the same radius. So I have same radius, two objects, but this one is a bigger mass. This is a greater mass, yeah, B. A has a greater weight, so weight is the FG equation, so M1, M2 over R squared. So greater planet mass would make a greater force, so that is true. The acceleration on, the object on A has a greater acceleration towards the planet, so G acceleration is big G M over R squared, where M is the mass of like the planet, the thing that's like causing the acceleration. So a bigger planet mass would mean a greater G, because this M is the M that got bigger. So that's true. And the object would have a greater mass. No, the object's mass isn't going to change where it goes. Only the weight, which depends on gravity, changes. Two identical spacecraft orbit the same planet, but at different radii. A orbits the radius farther than the spacecraft B, so same planet, A, this is B, right here, and then A is farther out, like this. And we're circling all that's true. A would feel a greater gravitational acceleration. Not true. If you go farther away, you feel less pull. B feels a greater acceleration, but not A. A has a longer orbital period. Yes, that is true, because if you have a bigger radius, you have a slower velocity, you take longer. It's what we wrote, the same reasoning for longer period, you want slower, so you want a big radius. So when I have a big radius, it is slower and has a longer period. A has a faster orbital speed. No, we just said it would go slower. B would go slower, smaller r, closer would be faster. And then A has a smaller force with the planet than B with the planet. And that is true, because if you were to plug into this equation, the force equation, then for A in the planet, it would be a bigger radius than for B in the planet. So bigger radius divided by bigger numbers would get smaller. And then lastly, the space shuttle orbits the Earth at an altitude where the acceleration is this. What is this shuttle's speed at this altitude? So you would have to plug into your G equation. We're orbiting the Earth, so you're going to plug in the mass of the Earth. And you're not going to plug in the radius of the Earth because it's some distance above, and I don't know how far above it is. So that's my unknown, equals 6.7. Multiply r squared up. Crosses off, divide the 6.7 over. That's going to give me r squared is 5.98e13, and then you need to take the square root, so my radius is 7733045. That gives me a radius. I want the speed, so I'm going to use square root of gm over r, 6.7. Again, mass of the Earth, because that is what I'm orbiting around, and now I know how big my orbital radius is, and now it's straight plug into your velocity equation. You get 7198 meters per second. Okay, hope you guys all got that. I'm uploading the answer key from warm up in class today and the whiteboard practice with answer keys. Study lots.